Hello, yeah. This is another video on machine learning using R. Today I want to talk about dimensionality reduction using shallow autoencoder. So first, the key points about autoencoders. So an autoencoder is a neural network that compresses data, we call encoder, then reconstruct it, we call decoder. So you got an input and output, learns to copy input through a smaller bottleneck or latent space. And it is unsupervised learning, no labels needed. Just minimizes reconstruction error measured by MSE, okay, mean square error. And there's three main uses. One is dimensionality reduction. Usually for shallow autoencoder, we want to deal with less than 50 dimensions. If you get high dimensional data, then you have to use a deep neural network. It can also be used for anomaly detection. Usually you can look at the high reconstruction errors, and those points are outliers. And you can do feature extraction, a latent space for other models. So basically, the architecture of autoencoder is input going to hidden or bottleneck, then go to output. And these should be the same dimension as the input. Okay. Another word on shallow versus deep. So here we are only talking about the shallow autoencoder. We are going to use neural network with just one layer. Okay, so it's very simple. And they're good for tabular or small data set. And if you have large data set or complex data set, such as images or big data, then you have to use deep autoencoder or deep neural network. And how to implement deep neural network in R is fairly complicated. I don't think I'm going to include them in this series of machine learning on R, using R. I'll try to generate another separate series on deep learning, deep neural network in R. Okay. All right, let's get started. So here we're going to use the neuralnet package in R, and also there's a mlbench. We need these two packages. Load them in, set random seed. We're going to create data set of 500 observations. And we're going to use lmbench.2D normals, generate the sample size, and we do two clusters, standard deviation equals 0.5, and then output a data frame. And you got x1, x2, and you draw this x3, x4. So we're going to have like 4-dimension to 2-dimensional. Okay, so this is really for demonstration only. Okay, and you can also notice that we scaled the data. Okay, all right. So then the true autoencoder will reconstruct all inputs from all inputs. Okay, so the formula would be x1 plus x2 x plus 3 plus x4 go to x1 plus x2 x plus 3 x4. So input equal to target. So this is the formula. Paste name, and then we get we use this neural net function to generate the autoencoder. Okay, the formula is the same as the formula we just constructed using the formula string. Data is a data scaled, hidden equal to C2, the bottleneck layer, got a 2-dimensional latent space, linear output equal to true, linear learning rate is 0.01, and stat max is 200,000. Okay, now the autoencoder is done. Let's take a look. Load it out. This is the neural network. You can see the inputs are x1, x2, x3, x4, and then you got the latent. This one layer, you got the latent. There are two nodes there, and then they output to x1, x2, x3, x4. Okay, so and you can see give you the errors and steps is 168,506. So it takes a long time. Okay, so you can imagine if you get a very high dimensional data set, it's going to take a very long time. What we can do is, okay, we can calculate the reconstruction error. So doing the prediction, using the autoencoder to predict the data scale, and reconstruction will be the raw means, and the scale the minus predicted, and square. And this is a summary, and kind of the mean is 0.002, okay. We can visualize the clusters in the original space. It look like that. So there's two clusters there. And in X1 and X2 space, okay? So then we can do some further analysis using this autoencoder. First is a latent space visualization. We can get the hidden layer activation and neural net source in model at rep. Okay, so get that hidden activation, and then it's a latent 2D from hidden activations from the first two neurons. Okay, and then we can plot the latent space with clusters colors. First, let's extract the hidden layer activation, and then we assign them into, I repeated this twice, but then we can plot it out. It looked like that. You can see there's some blue colors, some green colors, the dots, right? So this autoencoder latent space, the two-dimensional bottleneck. Okay. Second thing you can do with it is anomaly detection. Basically, you can calculate the reconstruction errors, and those points with high reconstruction error equal to outliers. Okay, so you can define the threshold, so 0.95 quantile, and you define which observations has reconstruction error greater than the threshold, and then this is the number of outliers, and you can plot them out. So basically, in these plots, any dots that with black color will be the outliers. Okay. Second thing you can do clustering on the latent space. You can load the cluster library, you do k-means clustering, and then you can plot it out. And also shows you, the membership of the clusters. So look like that. Okay. And then you can also evaluate reconstruction quality by cluster. So basically, you can just say, I want to calculate the mean reconstruction error, let classes equal to 1 and class equal to 2, and print them out. So you can see cluster 1, you get 0.0208. Cluster 2, you got 0.0194. If you're wondering, how do you tell whether this quality is good or not? Here's the rule of thumb for quality. Between 0 and 0.1 is outstanding. Between 0.01 to 0.03 is excellent. 0.03 to 0.1 is good. 0.01 to 0.5 is fair. Larger than 0.5 is poor. So our case is excellent. All right. You can also compare the reconstruction with PCA. Okay. So you can calculate the PCA result and the reconstruction, and then the MSE for the PCA. You can see the PCA MS is much larger than the autoencoder. Actually, the autoencoder beats PCA by 99.8%. Okay. All right. We can also put everything together in a summary table using this put in the data frame. So you get the method equal to autoencoder in the PCA, and another variable MSE, and then the outlier, the number of outliers, and then the improvement. Print it out so you can see it has the MSE for autoencoder and PCA. There's outliers identified by autoencoder, which is 25 outliers, and improvement baseline, and so basically it's 99.8% better than PCA. All right. I hope this is a good introduction to autoencoder, but this is the shallow autoencoder, and much more interesting autoencoder will be the deep autoencoders, and which are like deep neural network, which I'll try to make a series separately using deep neural network. Thanks.